Yeah, I'm Matt Weiss, part of the Cubism group at UMass Boston under Chris Fuchs. And you may have heard of an interpretation of quantum mechanics called Cubism. I'll have a few words to say about it at the end of the talk. But suffice it to say, a lot of the problems that our group works on are kind of conceptually or philosophically motivated. So yeah, characterizing quantum state space with a single quantum measurement. Little history. It was in 1927 that Niels Bohr introduced the idea of complementarity as the distinctive feature of quantum mechanics, that not all aspects of a physical system may be simultaneously definite. It was actually at this Como conference in 27, and then he prepared this paper in 28, which is definitely worth looking at if you've never had the opportunity to do so. And he discusses the classic example, the Heisenberg uncertainty principle. Given an ensemble of identically prepared particles, a small variance in position implies a large variance in the momentum and vice versa. And the way I'd like to phrase it is that regardless of the choice of ensemble, the variance of x and p can't be made arbitrarily small together while remaining consistent with quantum theory. And again throughout my talk, this idea of consistency and constraints on probability assignments is going to reappear. So if consistency with complementarity is the key, you might ask, could we think of quantum states, quote unquote, as quote unquote just probability assignments which satisfy appropriate uncertainty relations for all observables? And you can. And from this point of view, you might say that the Hilbert space formalism isn't fundamental. It's just a useful technique for imposing these sorts of constraints on your probability assignments. But there are other techniques on offer. We're used to thinking of quantum states as state vectors or density matrices. But as I'm sure many of you know, for certain special measurements, so-called informationally complete or tomographically complete measurements, the quantum state can be recovered from the Born rule probabilities assigned to its outcomes. This possibility wasn't really contemplated, as far as I know, by Bohr and Heisenberg, although I think Schrödinger had an inkling. Okay, so we might rephrase the question. Could we think, or is it profitable, is it productive to think of quantum states as just probability distributions on the outcomes of an informationally complete reference measurement? So I'll use this term, reference measurement, throughout. There's a catch, of course, which you might be expecting, which is that yes, all quantum states correspond to probability distributions, but not all probability distributions correspond to valid states. And in fact, the previous talk, in the question session, this sort of came up in the context of the lambda polytope. How do you actually identify the quantum states themselves? So what happens if you use this map to go back from probability distributions into Hilbert space, you find that some distributions correspond to matrices which are not positive semi-definite. And so you can't think of them as density matrices. And this sort of encourages the idea that you could think of quantum state space as a kind of special subset of the probability simplex. And the shape of this special subset will depend on the choice of reference measurement. So in this talk, we're going to consider one particular class of reference measurements, those which form complex projective 3 designs. And I'm thankful for David for kind of setting the tone, mentioning 3 designs on Monday. Such measurements are necessarily informationally complete. And so quantum states can be regarded as probability distributions. But also what really makes 3 designs special is that the valid subset of the probability simplex that corresponds to density matrices can be elegantly characterized by a kind of generalized uncertainty principle. And so we're going to sort of derive the shape of quantum state space, if you like, from a generalized uncertainty principle. Although it, in fact, will start by giving a simple geometric picture of pure state probability assignments themselves, probability assignments corresponding to pure states. And then finally, we'll relate our result in the spirit of this conference, to the Jordan algebraic structure of quantum theory. So just to get started, we're going to just go through what I'll call the reference device formalism. As you all know, a measurement, or a POVM, a generalized measurement, if you like, a set of positive semi-definite operators that sum to the identity. Informational completeness is just the idea that these operators span the d-squared dimensional operator space. And for an informationally complete measurement, the Born rule probabilities fully characterize the density matrix rho. I'll call a reference device a little bit more than just a reference measurement. It's a measure and re-prepare device. So the idea is you do an informationally complete reference measurement, and conditional on the outcome, you prepare one of an informationally complete set of reference states. And you can think about this in terms of like the Luther's rule if you like, but this is just a little bit more general. In particular, for purposes of this talk, again, we're going to focus on reference measurements that are 3 designs, and then the states will be 3 designs. We'll in fact take these reference states to be proportional to the effects. So certain probabilities will play a fundamental role for us throughout. And they arise when you consider, here's our reference device, and what happens if we take its reference state and feed it back into the measurement. And you can think about these probabilities, given that we've prepared state sigma j, what's the probability of getting outcome ei? Alternatively, you can think about this, given that we got reference outcome ej last time, what's the probability that we get reference outcome ei next time? Sort of using the outcome of the measurement as a proxy for its state preparation. And sometimes, out of laziness, we'll just refer to this stochastic matrix as just P. How do we recover a density matrix from probabilities? We have to consider a dual representation. And we'll do it in a sort of probability-first way, in a way that emphasizes that probabilities are the fundamental building blocks here. One way of doing this is to let bold E be the matrix whose rows are vectorized effects, and bold S be the matrix with vectorized states as its columns. And you can recover the Hilbert-Schmidt inner product in terms of a little bracket with these vectorized operators. And so you can see that we can concisely write this conditional probability matrix in terms of just bold E on bold S. And I should say, one sort of the significance, one of the ways in which this matrix is significant is, because the states and the effects are information complete, this conditional probability matrix sort of characterizes the reference device in its own terms. You can think about like the states characterizing the measurement, or the measurement characterizing the states. Okay, a definition. I'll call a Born matrix any matrix phi which satisfies this expression here, p phi p equals p. And if you know anything about the theory of generalized matrix inverses, this is a so-called 1 inverse. So phi will be a 1 inverse of p if it satisfies this equation. I think this, that sort of notation was developed by Penrose. It turns out that if your reference measurement, reference states are informationally complete, if phi satisfies this expression, it'll also satisfy this expression here, S phi E equals the identity, which we've taken to calling the Born identity. Okay, well, so this gives us a resolution of the identity. And so we can plop it right in front of a vectorized density matrix, and we can derive this sort of reconstruction formula here. We can write any rho as a linear combination of the reference states weighted by the probabilities, except after they've been acted upon by this linear transformation phi. Kind of the point of starting from this equation is that this equation refers only to probabilities. This is sort of the cubist spirit, if you like. Probabilities all the way down. Okay, everything, we want probabilities to be the building blocks of every expression. Whereas this identity requires that you know something about the Hilbert space representation. You need to have representation of your states, its density matrices, and so forth. Whereas this, you could contemplate just from your conditional probability assignments that characterize the reference device. Every matrix has a one inverse, so you will always be able to find a phi that satisfies that. Okay, so here's where the magic happens in this style of formalism. Suppose we consider an alternative measurement with effects AI, and we're interested in the Born rule probabilities. We rewrite it in terms of vectorized operators. We insert a resolution of the identity, and when bold E acts on rho, this gives you the vector of probabilities which characterize the state. When AI acts on bold S, it gives you these conditional probabilities that characterize this alternative measurement in terms of the reference states. And then phi is left in the middle. And again, notice I've used, instead of writing AI given sigma j, I've just used EJ, the outcome of the reference measurement, as a proxy for its state preparation. And the reason I do that is because when you do that, this sure looks a heck of a lot like the law of total probability. And as you can see, if you think about relating everything to your reference device, the Born rule appears as a deformation of the law of total probability, which is nice. Now, this is a quasi-probability representation, if you like, where we've sort of cleverly shoved all the negativity under the rug of this Born matrix, phi. So that's like the essence of the reference device formalism. I need to make just a couple more technical points, just because they'll come up later. A special case of this, of the Born rule here, is what if the alternative measurement is just the reference measurement itself? And so you see you get kind of a restriction, a constraint on your probability assignments with respect to the reference device. And one possibility is that your reference measurement, the effects form a basis for operator space, in which case this constraint is totally trivial, because in that case, the phi will just be the inverse of p. But it's necessarily the case that a 3 design has to form an over-complete representation. And so acting with p phi on a probability vector, this p phi will be a projector, consequently. And by a nice choice of phi, this will project onto the column space of p. Sort of consistency with thinking about the Born rule in this way means that we really only need to consider probability assignments that are linear combinations of the columns of p. One way of thinking about this is to notice that because of informational completeness, the columns of E, bold E, actually form a basis for the column space of P. And consequently, any vector that you get from Hilbert-Schmidt inner product has to lie in the column space of P, because you can just rewrite this as, okay, bold E acting on some vectorized operator. And conversely, if you have some X that lies at col P, then you can write it in terms of trace of EI on some operator, call it X tilde, which you can just see by rewriting this and bringing the sum into the trace. Okay, so think of the column space of P as kind of home base for us. We've already heard about designs several times throughout the conference, so I don't need to dwell too much on this. Suffice it to say, from the representation theory of unitary and symmetric groups, we learned that if we take the integral over pure states, the tth tenth power of a pure state, if you like, the tth tensor moment of quantum state space, then it's proportional to the projector onto the permutation symmetric subspace. This is such an incredibly useful result. A complex projective T design, or a quantum state T design, if you like, is then an ensemble of n pure states, some probabilities and some pure states, such that the average over the ensemble with the tth tensor power is the same as averaging over all of quantum state space. Some facts about designs. Lest you're worried about whether these things exist, they always exist for sufficiently large n. In general, it's a kind of a deep question whether for any given n, a particular t design exists in a particular dimension. But if you go to n large enough, you can always find a t design. T design is always a t-1 design as well. 1 designs are just rank 1 measurements, where the effects are just proportional to projectors, which you can just see from this. If t is 1, this will be the maximally mixed state. And so you have a bunch of operators that sum to something proportional to the identity. 2 designs are very powerful already. Examples include symmetric informationally complete measurements that correspond to these simplices with d squared vertices. The vertices are pure states, so it's sort of like very simple, beautiful measurements. There are 2 designs. A complete set of mutually unbiased bases forms a 2 design. They're necessarily informationally complete, and one way of sort of seeing that is that from the 2 design property, you can show that you're always allowed to take phi, the Born matrix, to have a very simple form. We sort of specialize to the case where all these probabilities here in the definition of the t design are just 1 over n. That's not like strictly necessary, but I will do it throughout, and it just makes the formulas nicer. And if we can take phi to have this simple form, here J is the Hadamard identity, the matrix of all ones, then the Born rule becomes simply this, which looks even closer to the law of total probability. Several people have spent many years basking in the glory of the simplicity of this. And this is related, if you like, to the optimality of 2 designs for quantum state tomography, an old result that goes back to Andrew Scott. The train of 3 designs, I would say, is under active investigation, in particular because they're really useful for classical shadow estimation, where the form that they take is unitary 3 designs, an ensemble of unitaries, where the integral matches the integral over the unitary group. But effectively, for our purposes, this comes to the same thing. And the reason people care is because they lead to estimators of expectation values with well-controlled variance. For example, the stabilizer states for a qubit, the complete set of MUBs in dimension 2, they form a 3 design. So do the n-qubit stabilizer states, and David and Huangjin Zhu have given very interesting constructions where you can look at the Clifford orbit of certain states and generate 3 designs. I won't really talk very much at all going forward about where 3 designs might come from. I'm just going to assume that you have one. But it's a super interesting question whether anything I talk about today might help understand the nature of 3 designs, how to construct them, and their properties. The preliminaries are done, and now we'll get. So like I say, we're going to start with actually characterizing the pure states. And we'll begin by asking a kind of operational question. Suppose we prepare t different states and send each into its own copy of the reference device. What's the probability that all t reference devices give the same outcome? I'll call this the agreement probability. Writing it out, you can see that it's quite possible because bringing the sum inside this trace, you have the sum over the tth tensor power of the effects. You might think, yeah, these agreement probabilities might take a very simple form if the measurement is an unbiased t design. Because we know what this has got to be. It's got to be something proportional to the symmetric projector. David showed very similar formulas on Monday. You can express the permutation symmetric projector as a sum of permutation operators. And using the swap trick, if you like, you can derive these expressions, and each term, in these expressions comes from a different permutation. And you can do this for any t. This I've just shown for 2 and 3. And we'll see that really 3 is the highest number that you need to count to. So if you think about this for a second, you can use those expressions to derive, so if you have a 3 design, bounds on these agreement probabilities. So these lower bounds here are achieved when the states are mutually orthogonal, and the upper bounds are achieved when the states are identical and pure, because in that case, trace of rho squared equals trace of rho cubed equals 1. And you can see that's really the building blocks of what we have here. So consequently, pure state probability assignments have to satisfy that their squares have to sum to a particular number, and their cubes have to sum to a particular number. And like I say, you could keep going, to any t, and you'd find that pure states have to live, if you like, on t-norm spheres for any t of a certain radius. But it turns out this is already enough, because there's this very simple lemma. The proof is very straightforward, just thinking about the eigendecomposition of the operator, that a Hermitian operator A is a rank 1 projector if and only if trace of A squared equals trace of A cubed equals 1. Just to reiterate what I just said, for t greater than 3, we can characterize pure states with respect to an unbiased t-design reference device by, we're dealing with probabilities, so they have to be greater than or equal to 0, they have to sum to 1, and their squares have to sum to this, their cubes have to sum to that. Also, we have a constraint that the probability vectors have to live in the column space of P. If you sort of follow the argument, we appealed only to probabilities given by the Born rule, and sort of conversely, you can show that if you have some probability vector and you decompose it into a part in the column space of P and the part in its complement, then the part that's in the column space of P, in order to be pure, has to satisfy these equations. So, this is interesting because, it gives you this sort of geometrical picture of pure states that at least when I first, came across it, I found, very unexpectedly simple. So here you see, in 3 dimensions, the p-norm spheres for p equals 1, 2, and 3. In other words, spheres with respect to the 1 norm, the 2 norm, and the 3 norm. The probability simplex is just this facet here, because we've constrained things to be non-negative. And so quantum state space is just the intersection of the probability simplex with a 2 norm sphere of a particular radius and a 3 norm sphere of a particular radius, which has this sort of distinctive rounding. You may know that if you go to p equals infinity, you sort of approach the cube. And then finally, you just have to restrict to this special subspace, the column space of P. And really, that's the only thing that depends on the actual measurement, the particular 3 design, if you like. Okay, so in a way, we're already done. We've characterized quantum state space with a single quantum measurement. We've characterized the pure states, and everything else is just convex combinations. But we can, for example, come up with an alternative characterization of pure states from the fact that for a normalized density matrix, rho equals rho squared, if and only if rho is pure. And so substituting our resolution of the identity into this expression, so in other words, we're going to sort of expand both sides of this in effects, you end up with this sort of hairy-looking thing. You get 2 copies of the probability vector because you have 2 copies of rho, and then at the end of the day, the EI hits 1 sigma j from the first row, another sigma k from the second row. Take the trace, and it'll turn out that each term in this expression is added to its complex conjugate. And so you really just have to consider the real part. Okay, but the magic happens because for a 3 design, you can actually express these, the real part of, sometimes we call this the triple products associated with the reference device. For 3 design, you can express these triple products in terms of the probabilities which characterize the reference device. In other words, this stochastic matrix P. And it's really easy to see that. So let M be the teeth moment of quantum state space. For t equals 3, we can consider this joint probability distribution. And again, using the same argument from before, we can write it out like this, using the properties of the symmetric projector. And this works for any reference measurement. Like E can be whatever you like. But for unbiased 3 design in particular, M3 is also equal to this. And so this joint probability distribution can be expressed entirely in terms of these conditional probabilities that we've come to know and love. Just putting it together, we can express the real part of the triple products like this, and then our condition for pure state probability assignments over here, equation 25, dramatically simplifies to equation 29. And it's sort of the third order equivalent of the phi matrix becoming really, really simple for the 2 designs. You have this, all these cancellations. And it's sort of fascinating, at least to me. You sort of get this property where if the reference is a 2 design, this matrix P acts really, really simply on probability vectors in the column space of P. It just depolarizes them. From the 3 design property, if you have a pure state probability assignment, then P acts really simply on the squares of the probability vector, like the Hadamard squared of the probability vector. And it also just sort of depolarizes it. And if you had a T design, basically the same would be true if you put a T there and this 2 becomes a T and you get a different prefactor. Okay, so we've got 2 different ways, equivalent ways of characterizing pure states. One gives us, if you like, this nice geometry. This one makes us think about the sort of magical properties of this matrix. But what about quantum state space in general? What about mixed states? And so it'll turn out that we can characterize the validity of any probability assignment as promised by an uncertainty principle. And to see this is not hard. We first just observe that rho being positive semi-definite amounts to, if we go over all Hermitian matrices X, trace of X squared rho, in other words, the second moment has to be greater than 0. And this is obvious because if you square Hermitian matrix, this will be positive semi-definite, and rho being positive semi-definite is just saying that, one way of saying it is that on all positive semi-definite matrices, it's got to be non-negative. Okay, but writing it like this allows us to play our game, and writing X as a linear combination of effects for some components X, little xi, and using our resolution of the identity for rho, we get this expression, which, again, this real part of the triple products rears its head again. So now we'll make an assumption to make things nice. So far we've considered, probability vectors that live in column space of P. What if we consider that these x's that describe the observable live in the column space of P? Well, like I was saying earlier, P acts very simply on the column space of P. And because of that, this expression, equation 33, massively simplifies. Or I should say, just the expression for trace of X squared equals rho. So a little bit of notation here. I've just used X squared on rho as shorthand for the sum of the x's squared times the probabilities, which also looks like a second moment. If you interpret these little xi's as numerical values assigned to reference measurement outcomes. So here, if you like, the numerical outcomes of the experiment are not the eigenvalues of x, you do a standard von Neumann measurement, the numerical values that you get out of your experiment are these little xi's. And I should just say that mu here is just the maximally mixed state. I'll just reassure you that the first moment here, if you just sum over xi on the probabilities, that's just the same as trace of x rho. In other words, the expectation value for if you're sort of estimating x with respect to a von Neumann measurement or a reference measurement, it's the same. But they differ in the second moment. And kind of very nicely for 3 design, you have this expression here that relates the second moment of x with respect to a standard von Neumann, a projective measurement, with the second moment of x with respect to the reference device. And now our technical point from earlier comes into play. If you have some real x in the column space of P, well, it's got to be written like this for some Hermitian matrix x tilde. The Hermitian part just comes from the fact that x has got to be real. And from the 2 design property, if the right-hand side here is non-negative for some real x in the column space of P, then trace of x squared on rho has to be greater than 0, where, just to be specific, x is just given by this simple formula, which again just comes from the 2 design property. And so we conclude if we range over all real x in the column space of P, if this expression is, if the variance of x, again, where the second moment is defined like this, the variance of x satisfies this lower bound for all observables in the column space of P, then rho, the probability assignments P, EI, rho are valid. So this is the uncertainty principle that characterizes quantum state space. A probability vector is valid if it satisfies the uncertainty principle for all observables. All observables in Hilbert space, but in this picture, that's equivalent to all numerical assignments of outcomes to the reference device that live in the column space of P. What it's really saying is that valid reference probabilities can't be too sharp, lest they violate this lower bound. I'll sort of now take a sort of philosophical step back. Okay, reference probabilities can't be too sharp. Yet those same reference probabilities might imply a sharp distribution for some alternative measurement. For a qubit, you say you're in a Z eigenstate, the reference probabilities that correspond to it have to satisfy this uncertainty principle. And yet, using the Born rule, involving our matrix phi and so forth, you can turn that into probabilities for, a Z measurement, which is sharp, gives you a sharp distribution. This is just a nice way of dramatizing the difference between classical and quantum because, classically speaking, any alternative measurement is just a coarse graining of some fundamental reference measurements, say, measuring the positions and momenta of all your particles. And classically, certainty is achievable for the reference. In principle, you could know exactly which point in phase space you're in. And moreover, you can't achieve more certainty about some alternative measurement than about the reference measurement. Because again, any alternative measurement is just a coarse graining of the reference. And this is precisely defied by quantum mechanics. Certainty is not achievable for the reference. You can't actually occupy one of the vertices of the probability simplex. And moreover, you can achieve more certainty about some alternative measurement than you can about the reference. All right, so the final thing I'll talk about is the relation to Jordan algebras, very briefly. So, here it's really an uncertainty principle where the trade-off, I don't know if you like, is among all possible observables. I guess like sort of I suggested in the first slide, thinking about quantum states as probability assignments that satisfy uncertainty relations, if you like, for all possible observables. I mean, another way of thinking about it is, the reference, like it's in a way, the reference outcomes themselves are the thing that there's a trade-off about. Say like comparing it to, say like a coherent state representation. The coherent states have this sort of saturation of the Heisenberg uncertainty principle. And so the reference outcomes themselves kind of represent that very trade-off. And here I think that it's sort of like similarly in that spirit. The trade-off itself is represented by the fact that you can't go too far to the boundary of the probability simplex. Okay, so the Jordan product. Yeah, I actually recently learned that Pascal Jordan was in fact from Hanover, although perhaps that's the most one would like to say about Jordan the person, if you read further down the Wikipedia article. Okay, so returning to this inequality here, if you like, we can sort of reshape it into this expression, where we've defined fancy L to involve these triple products, phi, and our probability vector. And the non-negativity of the second moment here is equivalent to the positive semi-definiteness of this matrix, fancy L. And that's kind of nice, from just this expression here. It's not like immediately obvious like how to check. I hand you a set of probability assignments, like does it correspond with valid state? Well, one easy way is to just build this matrix fancy L and just check whether it's positive semi-definite, just like you might check if a density matrix is positive semi-definite. What's really nice, again, as always, if you choose 3 design to be a reference measurement, then we can substitute our expression for the real part of the triple products, and we can see that you can build fancy L out of nothing but reference probabilities. The probabilities that characterize the reference device itself, and the probabilities that characterize the state with respect to the reference. But there's another interpretation of this operator. So I'll remind you that the Jordan product of A and B is just 1/2 AB plus BA, this sort of symmetric product. Under the Jordan product, Hermitian matrices over the complex numbers form a Euclidean Jordan algebra. So far as I understand, Jordan and Wigner and von Neumann were sort of thinking about these things in the earliest days of quantum mechanics. And the idea was to understand like what kind of variants of quantum theory were possible, whether they all sort of were related to matrix representations. And so they sort of abstracted properties of Hermitian matrices over C, quantum observables. And their abstraction was to just consider a Jordan algebra which satisfies commutativity and the Jordan identity. And the Euclidean part is just if you let L be the linear operator that takes the Jordan product, a Euclidean Jordan algebra enjoys this sort of compatible inner product. And Jordan, Wigner and von Neumann actually, it's a beautiful story if you don't know it. They very early on classified the Euclidean Jordan algebras, the simple ones, and they just relate to, if you like, quantum mechanics over different number fields, and another case called the spin factors. And later on I think it was the 50s, some mathematicians came up with a purely geometric way of characterizing Euclidean Jordan algebras. And so it's a very interesting story. And in Quantum Foundations, there's a wonderful paper by Alexander Wills called The Royal Road to Quantum Theory, or thereabouts. And he encourages people to think about this, a geometrical way of thinking about Jordan algebras. terms of something called symmetric cones, as a way of figuring out what assumptions you need to kind of stumble your way into reconstructing quantum theory. Okay, so there's this sort of background in terms of the importance that Jordan algebras sometimes play in quantum foundations. And they have a role to play for us as well, because if you think about representing the Jordan product in terms of probabilities, you find something interesting. Namely, okay, so taking the Jordan product of rho and tau is just the same as having L acting on the little vectorized density matrix tau. And we want to expand that whole thing in terms of probabilities. We'll insert our resolution of the identity. E acting on tau just gives us the probabilities that characterize tau. I've just sort of represented this as a vector here. And I'll define fancy L, looking ahead, to be E acting on L, acting on S. And when you work out what this is, it's easy to see that it's just this very same operator that we were considering before. So we have this interpretation, this operator whose positive semi-definiteness characterizes the validity of probability assignments, and which can be built out of probabilities with respect to the reference device entirely, is nothing other than a representation of taking the Jordan product with that state, expressed in terms of probabilities. One way of thinking about this is that the real part of these triple products encodes the structure coefficients for the Jordan product. This three-index tensor can be extracted from this joint probability distribution, where again, M3 is the third moment of quantum state space. And the essence of this observation was already made by David some years ago. In this context, though, we can go a little bit further and say, well, this joint probability distribution, because we've chosen our reference device to be a 3 design, can also be written very simply this way. We conclude that this conditional probability matrix, again, that characterizes the reference device in its own terms, is sufficient to characterize the Jordan product as well, and consequently, through this algebraic structure, the entire state space. Okay, so to conclude, we've shown that the shape of quantum state space can be characterized by a single quantum measurement corresponding to a 3 design. How? An uncertainty principle constrains the probabilities that one ought to assign to a 3 design reference device. Pure states have an elegant geometrical interpretation, and in line with the sort of cubist spirit, if you like, each term in our equations is grounded in probabilities. And even better, these probabilities refer to the behavior of just a single measured re-prepared device. This is made possible by the delicate interplay between unitary symmetry and the Jordan algebra of observables. The algebraic structure of quantum theory implies that the third moment of quantum state space really fixes them all, and therefore so does a 3 design reference measurement. And I'll just end with a little advertisement, in a way, for cubism. So this result holds particular significance for us as cubists. Kind of the central tenet of cubism is that quantum theory should not be understood as providing a description of physical reality. In a way, you think about cubism as kind of being battle-scarred over the decades of warring with Bohmians and many worlds people. Quantum theory is not a description of physical reality. It's a tool, like probability theory is a tool. We don't say, does probability theory describe the world? It's a tool that you use to make better decisions. In the same way, quantum theory helps you make better decisions. And in particular, it helps you make better decisions in a world, if you like, might say poetically, undergoing ceaseless creation. In other words, when you make a measurement, you're taking an action on the world as a sort of a free agent, and nature is free to create a response, which is your own future experience. Normative here is just this idea that, like with probability theory, it's a good idea to use it. It's something that you should use, you ought to use. This kind of language kind of goes back to Bruno De Finetti, of the De Finetti representation theorems, but also he gave this sort of beautiful series of arguments already in the 30s, where he shows that you can derive all the rules of probability theory, the things you normally take as granted, by appealing to Kolmogorov's axioms or something, just from the idea that a gambler wants to avoid a sure loss. In other words, gambler is going around, he's buying tickets, pay this amount if this happens, pay this amount if that happens. Maybe his horse doesn't come in and he loses money. He might also be inconsistent, incoherent, an idiot, and make a series of bets that will guarantee that he's going to lose money. And De Finetti defined a probability to be the amount of money, the price at which a gambler is willing to buy or sell a ticket that pays $1 if the event occurs. If you make that definition, it's not hard to show that the demand that the gambler avoid a sure loss is just that the gambler should follow the rules of probability theory. You can actually derive them. And in this sense, the rules of probability theory are normative. They're things that a gambler should consider, ought to consider, if they don't want to lose money. He's interested, if he has a stake in success, he should or she should follow the laws of probability theory. And as cubists, we look at quantum mechanics in just the same way, that it's all about consistency conditions between probability assignments, constraints, under the caveat that unlike in the classical world, we can't rely on the existence of a non-contextual hidden variable model pulling the strings. There's a wonderful sort of cubist manifesto by Blake Stacey, where he suggests that quantum mechanical constraints are in some sense the most symmetrical, compatible with what he calls vitality. And in any case, in my talk, I hope I've convinced you that these constraints might be understood as a fundamental expression of complementarity. So thank you very much.